Hi, again by request, we're going to talk today about random variables, expectation and variance of random variables, and how we compute those. And then we're going to work out problem 2.19. And then in a follow-up video, I'm going to talk about linear combinations of random variables. So, what a random variable is it's a variable that can have multiple possible outcomes, and each one of those outcomes is associated with some probability. So the difference between, say, random variables uh, here in statistics and variables elsewhere is that elsewhere variables um, can either have any value or only, you know, one possible value if we, solve for it or something like that. And in the context of statistics, we recognize that a variable could potentially take on multiple values, right? And our job, of course, is to make sense of these variables despite this uncertainty. And so, to clarify, also, this is section 2.4 in the textbook. And as usual, if you click on uh, the slides icon here, it will take you to a Google document with slides on this section. And you can read this or follow along there. So what I'm going to start with is I'm just going to start with the prototypical random variable, which is rolling. Oops. It doesn't do dots very well. So it is rolling dice. Right? And so rolling the dice is really like the baseline idea of what a random variable represents. And so when we do that, when we roll the dice, we don't beforehand know what the outcome is, but we do know what the possible outcomes are, and we do know the probability associated with those outcomes. And so the way we would think about this most likely is we would say, all right, the xi then represent the possible outcomes from this. I'm gonna let x is the outcome. It is sort of weird to write with this thing, and there is a probability associated with each possible outcome. And so the possible outcomes of a die roll are, of course, 1, 2, 3, I'm getting better at this, 4, 5, 6, and the probability associated with these probabilities is, of course, 1, 6, 1, 6, 1, 6, 1, 6, 1, 6, 1, 6, right? And so as um, as with data sets, some of our main concerns with random variables, particularly if our goal is to do anything predictive with them, is, we want to ask ourselves, given a random variable, what are the likely outcomes, and how much does the variable's behavior, how much is that likely outcome or average outcome determine the behavior of the random variable? In other words, on average, what occurs and how likely is that thing to occur? Do most of the events occur close to the average value? Do the events occur all over the place? In other words, we're looking for a measure of centrality and a measure of variation in exactly the same way we would with data sets. In fact, uh, the notions of mean, variance, and standard deviations don't naturally apply to data sets. They naturally apply to random variables. When you get a data set, the sample that you get is certain outcomes of the random variables. Meaning, for example, if I'm trying to guess the weight of guinea pigs, the weight of a guinea pig is a random variable because every guinea pig is different. And each time I weigh a guinea pig, it's just some output of that random variable. And then I take a whole bunch of them together. And what I'm trying to do with statistics is then figure something out about the original random variable, right? And since I can't weigh literally every single guinea pig on Earth, then what I have to do is some sort of statistical analysis on what might be the parameters of the guinea pig random variable. And we've already covered means, variance, and standard deviations for data sets, and so the natural analog uh, uh, concept is the mean and variance and standard deviations for random variables. So let's first start with the mean, which we'll call mu. Oops. But is often denoted, and we will commonly denote here as the expectation of x. So E of x is the random variable, that's the input, and the output then is the expectation of x or the average outcome of x. Now, it may be obvious just from what you know about a diagram that uh, what this outcome might be or what this average outcome might be, and yeah, uh, if you wanted to guess at it, it would be 3.5, right? Because um, well, the right way to think about this is since each one of the outcomes are equally likely, right? Then a data set that sort of captures the idealized version of this outcome, and this is just how we want to think about this intuitively, is a data set that looks like this. 1, 2, 3, 4, 5, 6, right? And so we say, okay, each one of those occurs equally likely. So if I roll the dice 6 times, then I kind of expect, I mean, it wouldn't be realistic if this actually happens, but sort of on average, every outcome should occur equally likely. If I roll the dice 6 million times, then I should be fairly confident that each one of these outcomes occur a million times. And then what's the average outcome of, a bunch of ones, twos, threes, fours, fives, and six, all who occur equally likely? It's 3.5, right? And so, um, one way we would like to think about that is maybe as just that computation. 1 plus 2 plus 3 plus 4 plus 5 plus 6 all over 6, right? That's how we would do it if it was a data set. But we should know that this is the same as 1 times 1 6 plus 2 times 1 6 plus 3 times 1 plus 4 times 1 6 plus 5 times 1 6 plus 6 times 1, 6. All right, great. Great, and now it's in this desktop version. So uh, let's assume we know what the outcomes of the die roll are. And so let me start over. I'll give you a second to pause and write this down in your notes. And all right, let's raise the board. So let's say another way to think about e of x is 1 times 1, 6 plus 2 times 1, 6 plus 3 times 1, 6 plus 4 times 1, 6 plus 5 times 1, 6 plus 6 times 1, 6. All right. And so this is more than just a trick of algebra, because what we look at here is like, all right, what are these first numbers here? It's 1, 2, 3, 4, 5, and 6. Those are the possible outcomes, right? Those are the different values that xi could have taken on. And then what are 1, 6, 1, 6, 1, 6, 1, 6, 1, 6, 1, 6? Those are the probabilities associated with those outcomes, right? And so uh, there's a natural way to think about what this value means. It's like, all right, 1/6 of the time, your outcome is 1. 1/6 of the time, your outcome is 2. 1/6 of the time, your outcome is 3. 1/6 of the time, 4. 1/6 of the time, 5. 1/6 of the time, 6. So on average, this sum will give you the sort of average outcome. And if we want to keep track of what that was, we have 1, 2, 3, 6, 10, 15, 21 over 6. Which is 3.5. All right. And which we already know. Now, this will lead to a slight, sort of complaint on my part with the nomenclature, because really 3.5 is not an outcome we expect from a die roll. There is no side labeled 3.5. So the expected value in this case uh, maybe isn't a fantastic name for this thing. Really, the proper name maybe should be the average outcome. But of course, I'm gonna try to stick with the nomenclature and notation that you will see not just in this text but literally everywhere, and so that it's not confusing. And so if I wanted to generalize this rule, maybe the general version of this fact is that the expectation of x is the sum of all the possible xi's times their respective probabilities. And so what we have here is that that's exactly what I have here. It's like the first xi, which was 1, times the probability that it's 1, plus the second xi, which is 2, times the probability that it's 2, and so on and so forth. Oh, I'm pointing at this thing like anyone can see that, right? 1 times 1, 6, its probability, 2, and the probability that it's 1, 6, that it's 2, 3, and the probability that the outcome is 3, and so on. And if we think about this, let's say your die is weighted, so 6 is more likely and the other values are less likely, then this number here would get bigger. These probabilities would all get smaller, and the overall result should be that the average die roll gets bigger, right? Because the 6 now contributes more to the sum, and the smaller numbers less than 6 contribute less to the sum. On the other hand, if the dice was weighted low and say 1 was more likely than all the other numbers, then all these other 1/6s become something smaller. The 1/6 here becomes bigger, and now 1 is the biggest contributor to the sum, so the overall average should become smaller, right? So hopefully that's helpful, and I'm going to erase this particular screen now, and bye-bye. Okay, so let me no, I need a little bit more space than that, unfortunately. Uh, Now hopefully we can see that. So this is the same picture we had before. Uh, that's not the greatest, but I do need the space. Okay, so uh, so this is back to original sort of description of the random variable of rolling the dice. And so what we want to talk about now we know what the average outcome is, but what we want to know is how spread out is the are the results. Because you can imagine I could easily make uh, a random variable with the same average outcome as rolling the dice with a lot less variation and another one with a lot more variation. So one that would be a lot less variation, maybe something like the xi's are 3.4 and 3.6. And those are both a half each, right? That clearly has average outcome 3.5, and that the possible outputs are going to vary a lot less than this die roll. On the other hand, instead of 3.4 and 3.6, I could say um, 3.5 times 10 to the 10th, 3.5, sorry, plus 10 to the 10th, 3.5 minus 10th to the 10th, 1 half, 1 half, xi, px equal xi. And yeah, that's obviously going to be also have average outcome 3.5, but now like 10 to the 10th is like, what is that, 10 billion? So it's 3.5 plus 10 billion and 3.5 minus 10 billion. So its outcomes are going to range pretty widely, right? And so just like with data sets, these concepts are kind of useless, or the notion of an average outcome is pretty useless on its own. You want to know how widely distributed the variable is so that uh, when we make predictions about the variable, how accurate they're likely to be. So the formula for computing the variance is the variance of a random variable x is going to be the expectation of x squared minus the expectation of x squared, which is there is a formal algebraic uh, justification for this that to show that this expression that you see here is equivalent to the definition of variance for data sets that we've seen before, but I won't get into all of the details right at this moment. Instead, we'll just go ahead and work out what computing this variance is like. So, what does it mean to be the expectation of x squared? Well, let's just take a look at our dice roll example here. If our possible outcomes are 1, 2, 3, 4, 5, 6, what are the possible outcomes squared? Well, the possible outcomes squared seem like there should be 1, 4, 9, 16, 25, oops, 36. Right? And so, if those are the possible outcomes, then, well, you know what, let me keep red. Then the expectation of x squared out to be 1 times 1, 6, plus 4 times 1, 6, plus 9 times 1, 6, plus 16 times 1, 6, plus 25 times 1, 6, plus 36 times 1, 6. Right. And if we work out what that is, then 1 plus 4 is 5, 14, 30, sorry, no one can see me again, 1, 5, 14, 30, 55, 86 out of 6. All right. Then the variance tells us, our formula over here tells us that the variance itself then is 86 out of 6 minus 3.5 squared. 14, 30, 55, oops, 20, 30, 55, 91. Over 6. Sorry about that. All right. And so we could go ahead and work out what 86 over 6 minus 3.5 squared is by hand, but I don't really think that's a great use of our time. So I'm just going to go ahead and pop over to this thing over here and say, all right, 91 over 6 minus 3.5 squared, 2.9167. All right. And then one last thing to note. With variance, of course, comes a sister notion, and that's standard deviation, right? And so just like before, the standard deviation of a random variable is exactly the same thing as the standard deviation of a data set. It's just the square root of the variance. All right, so then in our case, the standard deviation would be all of that. Paste 1.7078 something. All right, so hopefully that helped clarify where the notions of expectation and variance come from, and more importantly, why they're true. Maybe a little less so for variance, just because the details are kind of an algebraic nightmare to work out. But at least for expectations, that the formula for expectation doesn't come out of nowhere. Now, it may seem as if the computation of expectation variance is a sort of tedious and mechanical process. That's because it is. And It's my personal philosophy that anything mechanical is supposed to be done by machines. And if you're watching this video and taking this class, that must mean that you in fact have such a machine available to you. You're either on a phone right now or a tablet or a computer, and a computer is a machine that computes. That's the name, right? Computer. And so for things like this, you know, for the purposes of like calculating things like expected value and so on. So this is my website here. The URL is in the syllabus, and I've emailed it out before. We might have seen some of these other calculators pop up. Oh, look at that, expected value and variance. Let's go ahead and open that in its own tab. So in our example here, if we're rolling dice, 1 through 6 are our outcomes, and 1, 6 is the outcome for all of them. And so if you look at the side here, right, it gives you sort of a graph of the distribution of the possible outcomes and their respective probabilities. And if we go down here, the expected value, 3.5, variance, 2.916667, exactly what we found here. Standard deviation is 1.707825, 1.787825. All right, perfect, right? And so, this is a class on arithmetic, and I honestly can't think of any reason why it's worth anyone's time to sit here and crank out, multiplying a bunch of fractions by numbers and adding them by hand. There's really absolutely no reason to do that. As a human being, I think you want better for yourself for that. Let the machines do the boring computational part. And as a human, what you want to be doing is thinking big picture and trying to understand what's going on with these problems and why they behave the way they do. All right. So, in light of that, let's go ahead and go to problem 2.19 as requested. So, I'm going to go ahead and view it as a student. So, hopefully this is readable. So, in a new card game, you start with a well-shuffled deck, and you draw 2 cards without replacement, and if you draw 2 hearts, you win $80. You draw 2 black cards, you win $40, and if any other thing else, so, a heart and a not heart, a black card and not a black card, whatever, then you don't win anything. And the game is going to cost you $5 to play. So what we want to fill out basically this table, just like we were doing before, with all of the possible xi's and their probabilities. And we've associated each one of these columns with an event. All hearts, all black, everything else. All right, so let's go ahead and kind of think about what all of this might be. And so the first thing I'm going to do here is say, okay, yeah, what are the possible xi here? All right, what are the possible winnings? And remember, these are net winnings. So let's start with all hearts. Okay, if I'm going to switch over to black here, and I say, all right, if I get all hearts, how much do I win? Well, I win $80, right? But hey, I had to pay $5 to play, right? So I give them $5, they gave me $80 back, And that means I walk away with $75 more than what I started with, right? And so if we go ahead, uh, until I get a hang of writing with this thing that's going to always look terrible for a while. Um, I'm going to need some space here. $75 is what it looks like, right? For my winnings there. All right. If I draw two black cards, I win $40. So I give them 5, they give me back 40, right? And that means I walk away with $35 more than when I walked in. So it looks like the second random variable here ought to be, or the second possible outcome here ought to be 35. And the remaining outcome then out to be, well, I give them $5 and they don't give me anything, I lose $5. Then that seems like what that outcome should be. All right. So those are my xi values here. What about my probabilities? Well, what do I have to do to draw two red cards? When I draw the first card, it has to be red, right? Sorry, not a red, a heart. What's the probability of drawing two hearts? Well, when I draw the first card, it has to be a heart. So in the deck, there's 52 cards, right? And out of those 52 cards, 13 are red. And so what I want to say maybe is, all right, 13 is over 52 is the chance that I draw one red card. So not only do I have to draw, so 1/4 of the time, or 13 out of 52, I'm going to get a red card. And then out of those events, I have to get another heart. Sorry, hearts. And so in order for the second card to also be a heart, well, how many hearts are left? There's 12 hearts left, right? I already have one heart in my hand. And there's only 51 cards left in the deck. And so the chance to draw a second heart is 12 over 51, right? And so 13 out of 52% of the time, or a proportion of the time rather, my first card is a heart, and then out of those times, another 12 out of 51 times the second card is also a heart. All right. And then you can simplify this fraction, but I don't see the point of doing that. And then for the black cards, well, out of the 52 cards, half of them are black, 26 of them, right? And so the probability that the first card is black is 26 out of 52, right? There's 26 black cards, there's 52 cards. So when I draw my first card, 26 out of 52, or 1/2 of the time, that outcome is black. All right. And then I want to draw another black card. Well, I'm down one black card, I'm down one total card. So out of the 51 remaining cards, 25 of them are black. And I have to draw one of those to get the second prize, right? So we have now probabilities for the first and probabilities for the second. Now, normally, computing the probability for, or computing the probability for not drawing two hearts or not drawing two black cards directly is extremely complicated because there's a lot of possible cases. The first card could be a heart and the second card not, right? The first card could be black, the second card not. The first card could not be a heart, not be black, but the second card is or it isn't. There's a lot of possible cases here, right? Um, but rather than work through all of that, what do I know is that, okay, some of the probability time this happens, some of the time that happens, the rest of the time that happens, right? And so what we should note about probability distributions for random variables is that the sum of all of the possible outcomes or their associated probabilities, they have to be 1, right? Because that's 100% of the possible outcomes. So what this number is 1 minus 13 over 52 times 12 over 51 minus 26 over 52 times 25 over 51. Right? I mean, it has to be because the whole thing is added up to 1. And I don't need to go killing myself trying to count all the ways that that could happen if I already know all the other possible probabilities. All right. So, with that said, we can go ahead and actually maybe compute these probabilities. And again, I suggest using technology to help us out. So our 3 possible outcomes were 75, 35, and negative 5, right? 75, 35, negative 5, right? Because this is winning $80, but I had to pay 5. Winning $40, I had to pay 5. Winning nothing, and I had to pay 5. The chance of you getting 2 hearts was 13 over 52. Sorry. 13 over 52 times 12 over 51. All right. The probability of winning or of getting 2 black cards was 26 over 52 times 25 over 51. And then the probability of getting not those events is, well, like we said, 1 minus the first thing minus the second thing. Yeah, there we go. So we have our possible outcomes for a random variable. We have their probabilities. And so we get expectation, variance, and standard deviation. All right, so expected value, standard deviation. So the last question here is whether or not the game works in your favor or works against your favor. Now, there's certainly some chance that you could lose, right? I mean, no one's going to deny that, and the chance isn't bad, to be honest. But the average outcome of this game is 9.5098, or maybe 9.51. Let's say it's that. I remember what the XI are. They're dollars, right? So 9.51 means $9.51. Positive 9.51, meaning on average, when I pay my 5 and I get money back or not, on average that outcome is $9.51, which is more than 0, which means the average outcome is me walking away with a net gain of money rather than a net loss of money, right? And so that means the game is overall in my favor. I might not win all the time. I might not even win most of the time. But if I keep playing the game over and over, the average outcome is that I'm going to win $9.5 or $9.51 per game. So it works for me. All right, so hopefully that helps you work out not just problem 19, but some of the other problems involving expectation and variance as well. All right, we'll follow up with. I will follow up here then with a video on linear combinations of of random variables. Okay?